Hello, everybody. Good morning. Welcome to PLC2's webinar, FPGA Circuit Design Part 1. My name is Eugen Krasin. I'm your presenter today. Synchronous versus asynchronous. It's very, very important for us to understand the aspect of how should we design the FPGAs. If you do it not correctly, what the problem is? The problem is that usually, right after you entered your design, maybe using Verilog or using VHDL, and you run a functional simulation, usually what you will see, it works. It works. But this is not really the last word, because in the function simulation, we don't have any skews, we don't have any delay, we don't have any strange phase relationship caused by some delays. So this means it works. But this is not true for the real world. In order to make it correctly run, and in the real world, we have to follow some rules. It's not difficult, but you have to remember the rules. If you don't do it, you will end up with some design which actually looks good after entering and after the function simulation. But in the real world, it fails. It fails randomly, it fails this morning, and maybe the next time it will fail tomorrow afternoon or something like this. So, but we need to avoid this. And in order to avoid this, we need to understand the problem, and we need to follow some rules. So that's what be the agenda today. This means I will actually talk about the, synchronous versus asynchronous aspects, and then talk a little bit about the design techniques, which design techniques are involved here, and I will give you also some examples. Don't do this, but you do this, okay? And then some extra stuff like pipelining, some resets, okay? And just after maybe to have some more information, some designing with RAMs, which is very easy. It's also design with FIFOs, which is also very easy. So in this case, I hope I have enough time. Actually, I prepared an example here, and I prepared an example here, actually, okay? So this means we can look to this. That would be the agenda for today. Now let's start. So first, of course, first assumption, today's logic design is based on two assumptions. All signals are binary and the time is discrete. This means it's a digital world, okay? And this means now we need to understand there are two possible solutions to do our design. The first solution is, well, we could do it asynchronous. This might be, on the first view, the easiest way to do a circuit. Whenever you would like, maybe you have some signals, some events, and whenever happens something, then maybe you do even some logic which decode something and provide maybe an edge in order to register this flip-flop. And the same maybe happens here. And even better is you could also take the output of a register like here and do some combinatorial logic, and then use this to drive an asynchronous set or reset input. This is called a synchronous approach. We don't have one synchronous clock in our design. They are asynchronous. The phase relationship of this clock is completely unknown versus the phase relationship of this clock. Also, even caused by some delay maybe on the net. As opposite, we do have the synchronous approach here. Synchronous approaches means we do have a one master clock which runs in our system, and everything happens, for example, with the rising edge of a clock. Everything. So this means all the delays and most of the delays are hidden in a period between the clock edges. Okay, so these are the two basic approaches here. So this means let's look what happened if we what is so bad with asynchronous circuit. Okay, so I'm not telling you it's impossible to do asynchronous design. It is possible, but it's very difficult. You must take care very. You must be very carefully during your design. So let's assume we do have something like this. We do have a clock 1, clock 2. So these are the inputs, also the clock 3. These are the inputs, and we do have something like this. So this means this register is clocked with a signal X, and this register might be clocked with this clock signal here. But what you need to know, in the FPGAs, a delay is always involved. So this means this is a delay here, this is a delay. Also, the delay through the component itself is not constant. It will vary with the temperature, it will vary with the voltage, it will also vary with the speed grade, and with the the quality of the manufacturing process. So there's some variation here. So this means, for example, if you look to the signal X here, the signal X, even if the clock input is a constant, or stable, let's say stable, then X will vary depending on the temperature, on the voltage, and on the speed grade. Okay, so this means you never know the switching time point of this register because it will vary. So this means the output here will also vary. But again, this output might be maybe processed with this gate and form the output Y. So this means that Y would have even wider field of operation. The same, look to the clock 3. The clock 3 is also, runs through some combination circuit. This means we do have also some variation here. So now look to this register. You will never know, or let's say the time point, the data will be written to queue will vary depending on the environmental conditions like voltage, temperature, and speed grade. This means it's very unreliable stuff, and you have to make some precautions, let's say, to make it really run. It's not impossible, but it's very difficult to do it. This means if you use this circuit, it will fail. It will definitely fail, not during simulation, no, but in the real world. That's a big problem. So in the same point, if you look to let's say the opposite, the synchronous circuit. So let's mean that's a synchronous circuit. We do have a clock, which is a master clock. It's connected to all the devices. And now let's look, maybe look to the signal X, and maybe look to the signal Y. So what happened now? You see, again, based on the delay, on the complexity of the logic, based depending on the voltage, depending on the temperature, this means depending on the environmental condition, the signal X, here we go, will arrive, earlier or later here at the destination. And the same happens with the signal Y. But we don't really care. We don't care about the real arrival point because we are taking the data right here. We're taking the data here. Okay. So this means it could be the best case, it could be the worst case. We don't care. It works all the time, stable and repeatable, and we know really what's going on. The question is, but how can I be sure that we are taking the data exactly here? How can I be sure that the data are stable at this time point? Because it's shown here, the data are stable. But how can I do this? Well, this is one of the, I will explain to you how this happened. This is one of my next webinars. It's a webinar for the timing constraints. So the idea of timing constraints is exactly this. We specify the period of our clock, and the tool and the design tool makes sure that this will exactly happen. And if not, I will get a report and have the chance to analyze and to correct my error. So that's actually the message. go ahead and use synchronous design instead of asynchronous design. So this means that the synchronous design methodology actually is just a definition. All flip-flops even use the rising, the same edge, rising or falling edge. You could. Of course, it's also, I don't think it's really violating the concept of synchronous design. Do something like this, you know. You have maybe something like this. So we use a rising edge here, we use a falling edge here. You could do this. It's not violates the idea of synchronous design, okay? But the problem, what would happen is we simply would double the requirements of our speed, because in this case, the time here is just a half of the period. So, okay, but let's say in general, falling or rising edge, okay? And you should, of course, when you partition your design, maybe partition the hierarchy, maybe in order to do it the way to minimize the number of connections. This means if this is the block A, this is the block B, and we do have maybe the clock buffer which runs here and here. It's okay, but when you do the partition, the hierarchical partition here, it's your decision. Just try to minimize the number of connections here. This helps the tool to find a better solution. And also register the output whenever it's always a good idea. Register the output when you're leaving the block. Then that gives you the best chance actually to meet your timing. Okay. Also, very important, synchronize. We'll also talk in this webinar about this. Synchronize asynchronous signal to a signal clock. This means if you don't synchronize this, you will have an asynchronous design, because you will use this asynchronous signal maybe to do something. No, you should synchronize this. Okay, and then we need to talk about CDC. CDC is clock domain crossing methodology, and again, this is one of the webinars I'm going to talk about clock domain crossing and how to do the synchronization circuits. I think this is a webinar, maybe it's the overnext or something like this. So, but what you don't actually not allowed to do not gate clocks in RTL. So what is gating clock? That's not allowed. You have a flip-flop here, and then maybe have some end gate, and you have here, let's say, a clock, free running clock, okay? And you would like to gate it, to switch it on, and you switch it off maybe. So this is not allowed. This is not allowed because you will actually suffer from the delay associated with this net. So there are other ways to do it. A little bit later, I will show you the solution for this. Okay. Do not create derived or divided clocks. Okay. What you shouldn't do, something like this. You have your counter here, counter, and then you use I don't know, maybe Q0 for binary counter, and run this as a clock. Okay. Even it looks good. No, it's not allowed. Okay. There are better ways to do it. So this is called do not generate derived clocks. There are better ways for you to do this. Okay. Do not create ripple counter. This means if you would like to have a counter, then the counter have one clock. A ripple counter looks like this. You have a flip-flop here, and then this is the toggle flip-flop here, and then you invert this, and you connect this to the next. Again, a ripple, again the toggle, and again. So this would be a ripple carry counter. You generate the clocks, okay? And you see that's the problem, because we do have a clock 1 here, we do have a clock 2 here, we have clock 3 here. So this is a completely asynchronous design, because you never know the value. When is the value of the counter stable? So this is not really allowed. Please don't do this. And we will talk about the set and reset. There are some special things we need to know. So that's actually the methodology. What happens? So this means if we, let me check this one here. One second, please. So just have to move it here. So this means again, what is the next biggest advantage? If you run a synchronous design, we have one clock. The timing analysis for your complete FPGA is very, very simple, because the tool will analyze all the delay from here to here, find out what is the biggest, longest delay, and calculate what is the maximum frequency for our design. It happens in seconds. But if you do an asynchronous design like here, it's very difficult for us to do a time analysis, because we never know really what is the action time, let's say, or switching time of this flip-flop. It depends. In the best case, it will switch early. In a worst case, later. Again, this might be in a reset. So this means in the best case, this register will be cleared. So this means before this clock arrives. In the worst case, this register, the reason is not here and the clock is there, this means the flip-flop will switch. So this means this is very, very bad, very, very difficult. Don't do this. But the synchronous design has a lot of advantages, yes, but we need also to care a little bit. We have to do it correctly. Let's assume, let's look to this one. We have a shift register, maybe a shift register. So it's a flip-flop 1 here, okay? Flip-flop 2 is here, and flip-flop 3 is right here. Now let's assume we do have a clock running and connected here. Now we are distributing the clock, but we don't do it really good. This means the delay from here to here is 3 nanoseconds. The delay from here to here is 12.5 nanoseconds. Okay? And the delay from here to here is 3 nanoseconds. So this would be a very, very bad design. But if you do it not correctly, if you do it wrong, it might happen. So this means, what happens now? If we would just, maybe for the first thinking, just ignore the delay times, then that's actually what we expect. At this clock edge, QA will be set. The next clock edge, QB or QB will be set, and at the next clock edge here, QC will be edged. This means the data runs through the shift edge. So that's what we expect. But now let's analyze the skew. It's called a skew. It's a clock skew. It's one signal, but there's a skew, it's a delay at a different arrival point of the signal. Then you will see it will be completely different. This means at the first clock, the data will be clocked to the flip-flop 1. QA will be clocked, but this clock edge is delayed a lot, because it's 12 nanoseconds later. This means the second flip-flop 2 will clock already the new data in. So this means that the function is completely wrong. And then just imagine, again, it depends on the environmental condition. If you have a worst case, so this skew values might be small, so the shift register might work. But if you have a worst case condition, long delays, then you will get, then your circuit will fail, and you don't really know what happened. My circuit failed. What happened? So this means that's the problem. We have to maintain a proper clock signal. And how can we do this? And that's now the point. All the FPGAs, also all the AMD or Xilinx AMD FPGAs, 7 series or ultra scale, they do have, just in order to avoid this problem, okay, they do have very, very special buffers. Okay, and this buffer is called buff GCE, buff G control, and buff G diff. And this buffer are there in order to do this. You have some flip-flops here, maybe something like this here. And then you have a clock signal here. And if you do the following, and if you connect a buffer, one of the buffer, right here, and run the clock signal through this buffer, then it's guaranteed that skew between this register are almost zero. This means it will not fail, and that's good. And there are 3 different types. they're a little bit different in FPGAs available for us. Let's have a look to these buffers. The one is the buff GCE. So this means this buff GCE, it's a very nice buff actually. You can enable and disable this. This means you have a clock here. But by playing with the clock enabled, you can the output, you can switch it off. You can decimate the clock. You see, that's actually the good way to decimate the clock or to do the clock gating. But this is done not through a gate. This is done using a very, very special element, BuffGC or BuffG control. That's a very, very flexible element. In this case, you can do, it's just a basic, let's say, template. You can do a multiplexer. This means you can do something like this, so you have here a multiplexer, clock 1, clock 2, a cell, and here it's without, for example. But this is not just a multiplexer described, as a gate, out of gates. No, they're a very, very special buffer. So in this case, you see here in this case, this is just a definition of switch it on or switch it off. So there are several ways for us to do this. This means look to the data sheet, look to the description of this BuffG control, or in one of my next webinars, I'll talk in more detail about this kind of buffers, or BuffG CE diff. That's very nice. This is actually a buffer you can actually apply, a clock input, and then give us give the parameter for the divide parameter, and you can actually divide with this, using certain values, divide the clock. Okay, this is again the proper way to generate, to derive maybe clocks. There are also another possibilities. You could, for example, use a PLL or MMCM to do the clock, to divide the clock or synthesize the clock. But this is actually a very easy way for us to generate a divided version of the clock. And this, what you see here, this picture basically shows the layout of the FPGA. And so these are the regions. Okay, so these are the simple regions, and the buffer are always contained in this column. So this is the column, and the buffer may be routed to all of the regions, and there are virtually hundreds, for the ultra scale, hundreds of clock buffers available, and clock regions available. For the 7 series, we do have 32 clock buffers available. So this means also, they are not just, if I go back here, so we are not only, buffer in this IO. This is the IOB, IOB line here. Not only the buffer, there are also PLL and MMCM part of this, very, very close to these buffers. So if you look to the MMCM and PLLs, you see we do have two kind of per region, actually, two kind of elements here. One is we have one MMCM and PLL. For the 7 series, we do have always one PLL and one MMCM. Okay. For the ultra scale, we do have a lot of MMCM, but also two PLLs. This means this is actually part of this IOB column, and there are again hundreds of such elements here. So this means use MMCM, for example, in order to input with a clock here, and then generate different clocks here, different phase, different frequencies, synthesize it up, synthesize it down, and that would be the relationship. Output is the input clock, the output frequency is the input frequency multiplied by M divided by D times O, and M and D and O are integer values, and by playing with the different values, you can actually synthesize a lower and higher frequency. So this is MMCM. So this is a digital version of a clock management. But we do have a second one. It's called a PLL. So what's the difference between the PLL and MMCM? In the first view, it actually looks very, very the same, because you see, the relationship between input and output is the same, but the values are a little bit different. They are smaller. And what's the use case? The use case for PLL is actually our dedicated frequency generation components for memory interfaces generated and implemented in FPGA. You know, especially today, DDR3, DDR4, they need very, very accurate, very, very high frequencies in order to operate correctly. And these elements, the PLL, are used for this. This means if you implement a memory controller, so this means this is your FPGA. So you have this row here, and you have it here MMCM PLL, MMCM PLL, a lot of them. Okay. So if you implement a memory DDRX memory here, then this this PLL is already used because it's dedicated. But you can use MMCM. But for example, here, if you don't implement here a memory, then you can use the PLL and you can use MMCM for your internal circuitry. So this means if memory controller is implemented inside FPGA, the PLLs are used for this. If not, then the PLLs are available for you to decide. So now, what is the 1 second here? Okay, what is this now? So this means now let's look to the design techniques itself. So we know already this. That's the big problem. Whenever we would need to connect sequential elements, this means synchronous design. We need to be aware of this. In the ideal situation, that's okay, because ideal means no delay at all. But this is ideal. This is real. But in the real, we do have a delay here. Because we do have a delay, there's a skew between this arrival time and this. Is a skew because of this delay. Okay, and now we need to be able to deal with this skew. Okay, if we do something like this, a shift, and this is actually the worst case scenario. So we do have two flip-flops talking to each other. We do have a clocked output, let's call it TDQ, and we do have a connection of these two flip-flops, and we do have a delay time in between. The problem is if the delay time, the condition for proper capturing the data, the delay time must be less than this clocked output. If this is not true, this condition, then this flip-flop will capture the wrong data. As you see here, if there's a this is the input clock, and this actually the second clock here, and this is delay. So then it may happen that because if the delay is big enough, we will capture already the new data, not the old data. This means we're missing the shift transfer capability. So this is bad. So we need to avoid this. Even if you look to this picture, even if we have some combinatorial logic here, so this is the standard situation, it makes it easier for us because now the condition is it's the T delay we can allow us is it's a clocked output time plus the combinatorial delay. So it's easier for us to do it because we have more delay time. Okay, but even a problem, still a problem. We need to make sure it will happen. So what's the solution? And that's the solution. You have to put here above G. So this is one of the buffer what I showed to you. Buffer. These are one of the different types of the buffer. If you put this if you describe this, you do maybe instantiation or the synthesis will do it automatically for you, then it's guaranteed. There is no skew which is available or which is implemented here or which is present, and your circuit will run. Okay, so that's a big point. Okay. So this means just again a summary. Okay, that's what you already know. Just a summary. Okay, use just one clock. Okay, and do not, just a summary repeating here, do not do something like this. Use buffer, clock buffer, the special clock buffer, in order to implement this function. Some examples. Even it's the first idea I would have. Okay, so let's assume I have a external frequency of 100 meg. Okay, but internally I would like to have some flip-flops. They should run with 50 meg. So in this case, I say, that's easy. I just take the 100 meg, go to a toggle flip-flop. For this is basically divide by 2, and connect the flip-flops. And now the flip-flop running with 50 meg. I know I will not have any skew problem here, because I know I'm using a clock buffer, so that's correct. But what is not correct? But what is still the big problem? If this circuit would be something like this, then okay, it will work. But usually it's something like this. You have your master clock, you have some logic which is a clock with this internal clock, generated like here. But if you later on maybe would like to compare, to do something like this, to use again my master clock or the first clock to register data, this will fail again, because the relationship, the phase between here and here, that's actually not known, because you have a delay here, you have a clock to output here, and you have a delay here, you have a delay here, so it's not known. So this is not correct. Do this. That's very easy. Just use this as enable now. Okay. Now it looks like this. This is your master clock here. Now this enabled signal, it's called an enable, looks like this. This means this flip-flop will be clocked at the, so in this case would be here, clock, for example, right here, because it's an, so this means we really don't care about the delay. So this delay time here, we really don't care, because we do have a complete period time to propagate the signal. This means all these two flip-flops, they will actually clock at the same time, because it's just used as an enable. It's very, very reliable, and very, very nice situation here. Or something like this. Don't do this. Yeah, you have maybe two external clocks, even they do have maybe a good relationship, 150 meg, but you don't know really the phase. Because you don't know the phase, this is always wrong, because we'll always usually violate the signal here, because this counter runs with 100, but you use also this clock to capture the compare result, but you never know the phase relationship, so you will end up with setup and hold. So this means, again, in this situation, very simple, just do the same. Just always try to minimize the number of clocks. You can do this. Of course, alternative would be you replace this one through a PLL. So in this case, then you can have one clock, maybe 100 meg in, and two clocks, 150 out, and the PLL will maintain the phase relationship between. So this is okay. So, but this one is bad. You could use a PLL, or you could use something like this. Or that's what I don't know. I remember maybe I remember a few years ago, the customer they would like to do this, and here actually it fails all the time. Here's a sensor, and the sensor, they provide some clocks, maybe different clocks. Okay. And the idea was actually to use the signals and to count here, and then finally capture the different values and do something like this. And the sys clock was actually there to output the data to to other systems. It's a big problem, because these clocks are completely asynchronous. It's not a deal. It's not a problem with the counter, because they're using a global buffer. So the skew is okay. But this will not be okay, because these signals, that you don't know the phase relationship. So this means this will fail. Okay, so in this case, what we usually do, and that's one of the standard solution, we just use useful edge detection circuits. So this means in this case, that's a standard, let's say, standard component for synchronous applications. You know, we have an input signal here, for example, okay? But instead of using this signal as a clock, we just run through the edge detection, and we provide a pulse, which in this case would be the rising edge. This means whenever there's a rising edge here, so we will get a pulse, which is completely synchronous to the clock. So this means you can very nice do the analysis. So this would be for the rising edge, and this would be for the falling edge. I just change this component here, and this would be for both edges. Okay. So, and if you do this now, you just take this rising edge function right here, and now we will actually synchronize and capture the signals to pulses. And now, of course, everything is run with sysclock, and now it's okay. So, and this, of course, will there are a lot of different application and situation we could do actually. We could do this kind. This is just one very simple example. Okay. Oops, 1 second. Here. Also, this one. You would let's assume you would like this account, okay, and you would like to register, you know, some value if the counter reaches the value 15. This means 1111. So usually you could do this. But let's assume that we are routing these elements. This means the delay here is different than delay here, is different than delay here, different than delay here. Let's assume we do have a shorter delay on this. It's just a question of, you know, it's possible. Okay. So this means if they have a shorter delay, okay, then this means if the counter, for example, counts from 7 to 8, because of the shorter delay here, the upper value is already there, but the lower values are still there. Then we will see very short time the value 111, and this gives you not the real pulse, which maybe looks like this. No, this gives you a spike, and this spike, you know, will actually trigger the flip-flop. That's wrong. So in this case, just do simple stuff, very simple. Instead of decoding the 15 F, just decode E and use this for the enable. So this is just one cycle before. That's it. Will always work. Very simple. The same, of course, you should do the same if you would like to use asynchronously. Don't do this, because again, you will get a switch, a glitch here, a spike. Then your register will be clear. No, just again go to the E, and then use synchronous, because now the spike doesn't matter if you have a spike, doesn't matter at all, because it's a synchronous. It will work all the time. Or for the example for the microcontroller, let's assume we do have something like this. We do have address bus, simple data bus, and write strobe, just to keep it simple. That's all. And I would like actually to access the data, to have to implement a register, write register. Okay, so then I could do something like this. Okay, I could actually this data bus from the microcontroller here, and that would be my FPGA right here. Well, I take the address bus, I take the write strobe, and whenever the write strobe is here, it's going up, I will get an edge here, and I register the data. And now the data bus is right here. Because this has a no phase relationship, no phase relationship at all to my master clock and FPGA, I need a synchronization register, otherwise it will not work. Again, this will be discussed in the CDC section of the webinar series. But this application, it will work in the maybe in the function simulation, but not real, because the problem is, you see, this would be a wide combinatorial function. This means usually what the microcontroller have, they do have a hold time very often almost zero. This means even if you have a wide function, then it takes some time to decode the rising edge or the right slope. This means the decode pulse might be somewhere here, and we are missing the proper data because of the hold time requirement. So that's not very good. So this means we should maybe do something like this. So if you do this, it's much better. Then you can actually use the proper address to enable this and use the right stops. In this case, there's no logic, and then we will meet the hold time requirement when of course we still have to synchronize this. So this means this microcontroller have, actually if I go back, two possible solutions. First, we could implement asynchronous interface, which is okay, or we could implement a synchronous interface. So that would be asynchronous interface. It's not good, it's bad, and that would be also a better asynchronous microcontroller interface. A lot of people actually are doing this. It's okay, it's not bad, it will work. But you of course have to synchronize this. Or we can do it synchronous, and in this case synchronous. We just have my master clock here, and now we're actually again using you remember this is again the edge detection. Using the falling edge detection circuit, we just capture the right, so generate the right enable pulse, and then use this to to capture the data. And this is basically to decode the proper address. And again, that's a pure synchronous design. It's very, very nice, it works, but what's the disadvantage here? So the disadvantage is usually it's not a zero weighted application, because we will need a certain width of the right stop. If I go back for this one, in this case, it is a zero weighted application because we are taking the data immediately and don't have to wait. So that's it's your choice, whatever you like. Okay. So these are the applications here. But again, we need to pay. We do pay a price for our synchronous stuff. So let's say if this is your circuit, okay, and first assumption, this is this block diagram. No global, see, no global buffer. So in this case, if you try to analyze the maximum frequency of this design, so this means the maximum time here is TA, the time from here to here is TB, and the time from here to here is TC. What is the maximum frequency? Well, in this case, it's the FCLK would be 1 to TA, for example. This means one reverse of the biggest time. TA, what's bigger? TA, TB, TC, and the biggest time actually define the frequency. So, but this is not real, because we need, in order to avoid the skew, we need to have a buffer. So now I have a clock buffer here. Here we go. So now if I insert a clock buffer here, I will actually manage the skew. It will work all the time. But what is the price? I have to pay a big price, because this buffer causes a delay. It's a delay. Okay. Then this means the clock here versus the clock here. There's a phase relationship. This means this clock arrives earlier than this clock. This means where I have more time. So this is good. So this is very good. I have more time available here because the clock arrives later. This clock buffer is neutral for this pass. But you see the problem here, because this clock arrives later than this clock, which captures the data. I'm missing the delay time. So this means the specification in this case would be the problem, that my delay through the buffer will actually decrease my maximum frequency I can achieve from an FPGA. Now that's a standard problem we know since 20 years. Okay, so but what is the solution? How can we again improve the FCLK and still having the buffer? And again, that will be part of my next webinar. So if you use a PLL here, you know what PLL is doing? The PLL is actually has all the advantages of a buffer, skew, no skew, but have the advantage of the phase relationship. This means the phase of this clock will be the same as this clock and the same as this clock. This means using a PLL will actually again we'll say, correct the disadvantage of the global buffer. Again, that's why we very often use a parallel for synchronous application to optimize the clock to output behavior of our FPGA. Pipeline. That's very simple. The pipeline basically means, okay, you have a clock here, okay, and if I use one clock, I have just one period here time to run through this logic. This means, let's assume I have just a very big time, 10 nanoseconds delay here. Or then I would have, just ignoring clock output and setup time, then the frequency would be, 100 meg, because 10 nanoseconds period is minimum. So, but if I just split this into halves, then I have a 5 here and 5 here. Now the frequency would be 200 megahertz. Okay, so this means that's the whole idea. By cutting the logic levels by using flip-flops, you will increase your frequency. For example, I have some design here. I have a flip-flop and I have a destination flip-flop here, and I have actually 4 LUTs. This means this is a pass 1, 2, and 3. And in this case, if I have 2 logic levels, or one logic level is actually run this one, LUT is on logic level. So I have 2, 2, and 2. So this means in this case, if I implement this, I would have a maximum frequency of 251. But if I insert a register right here, now I just double the frequency. Okay. Of course, what will happen? I will increase the latency. The latency will be increased, but the throughput will be doubled. For example, I do this. I have some data, A, and B, and C, and D, and now I just do multiplication, and this is actually the result. If I do this, then I have throughput 1. This means what is a throughput? Is how long does it take to get from the new value, the result is just 1 clock. Okay, latency is 1. This means 1 clock, but the maximum frequency would be 76 for given technology. So if I do this, if I just insert a pipelining here, then you see the throughput is the same, but the latency is 3. It takes 3 clocks, from the input to the output. It's called the latency. Okay, but the frequency, it's double, and the bit rate, for example, is much higher. So this means usually the latency usually not a problem. When you will do image processing, audio processing, even DSP, whatever DSP, different kind, the latency is not a problem. There you can actually live with the latency. There are only a few circuits which actually have a problem with the latency. So just think about this. Reset. Let me check. Okay, a little bit more. So the reset. Just a few words about the reset. Actually, very few design require reset on all register. Very few. And the resets are actually used to usually to put the circuit in an initial state. That's actually what we need. Okay, and there's one element for us in the FPGA. It's called the GSR. Whenever you switch on, you configure your FPGA, you will get a global set reset, and all of the internal register will be cleared. Okay, so. But in some cases, you would like to have maybe something like this. You have the FPGA, okay, and you have just block A, but maybe you have a clock B, and especially for this clock B, you would like to have a reset signal. Okay? It must be asynchronous. If this is the case, that's recommended. You should use a so-called reset bridge. This reset bridge works asynchronous, is asserted asynchronous, but it's deasserted synchronous. It's called a reset bridge, and that's that's a strong recommendation to use a reset bridge if you would like to use an asynchronous reset. But the general message: don't use asynchronous reset. But if you need, use a reset bridge. Okay, so this means, do I always think, do I really need to clear to reset? Do I really need to spend the reset signal to clear this bit? Should I do this? Or maybe it's maybe we don't need an asynchronous reset, or you didn't need a reset at all. Okay, for example, for shift register, it makes not a lot of sense to clear the shift register, because next time you are shifting the data, it's already initialized. So is it really needed? Okay, that's always the big thing. Okay, and also don't use a global reset which is connected to all of the registers. Use local resets. Okay, because local resets are very easier to implement for the tool. Okay, this means best is no reset at all, because you don't have no reset, you don't need to optimize the timing, because reset must also be optimized for timing. Okay, and this because you have no reset will of course improve performance of your FPGA. Okay, the design will be smaller. Okay, and also it allows you to use functions inside the FPGAs which would be usually it's not possible to do this. For example, this one in the FPGA we do have shift registers which are built-in components in the lookup tables. This means lookup tables may be used as shift register. But if you look at the symbol, there's no reset. You see, there's no reset at all. This means even if you describe a shift register, the tool would like to implement this using this very effective, using this internal component, but it's not possible because there's no reset. This means if you do this, and just go back, okay, if you don't use the reset, there are a lot of special components which might be used. If you use a reset, these components are not available for you because they don't have a reset. Okay, so be careful here. So this is basically the definition of the reset. In Verilog and in VHDL. So that would be in Verilog, and that would be VHDL. That would be no, sorry, that's here Verilog, that's VHDL here, and this would be the asynchronous reset, because we are asking reset first, and that would be the synchronous reset because we are asking the clock first. That's how we actually describe the different kind of flip-flops. And also we do have so this means don't use the reset if you need a special value to be initialized in the FPGA. Just describe your signal Q, for example, and define during the declaration, define the initial value, and this will be used after power. Of course, if you also additionally describe a reset, you can override this value. But in this case, maybe you don't even need an asynchronous reset for doing it here. So this means what you can do just in our FPGA. Let me do this way. In our FPGA, we do have something like this. This is our FPGA here. Okay, so and yeah, and we do have a very special block, and this block is called the startup. So this is the startup block here. This is the startup block. So what happened? And there's always the startup block is always there. This means whenever you switch on the FPGA, you configure the FPGA, this startup block is connected with a signal called GSR, Global Z Reset signal. It's connected to all the flip-flops, all the registers in your design. And if your configuration is done, this block is switched off and your FPGA gets initialized. But if you would like to have this function as a global function also during the normal operation, you just instantiate this startup block to your design, and now just connect here. Where is it? Startup. There's I don't see it here. Here. We just connect this signal here to a pad. That's it. That's all the connection we need. But if you connect this reset here, and then this block will stay alive even after the configuration. And now we can actually activate this and deactivate this, and we will get a global reset without actually spending local routing. Okay. But again, this is no local. It's always global. It's always a complete FPGA. Okay, so and that's a recommendation. You see here, if you don't do this and you describe your Verilog or VHDL and all your processors have a reset, okay, then that's highlighted white. You see a lot of routing channels are just used for the reset. You're wasting a lot of resources. Maybe you don't need this, okay? This means use local reset, and if you can live with a global reset, okay, you can actually use the startup to do this. That's actually the whole idea. And that's the reset timing path. What that's the alternative. What you can do? Let's assume we have a we do have asynchronous reset here. Now we have a reset bridge, and you see this is synchronous. This means this is the clock, and this pin is maybe gets something like this gets. Let's assume this was low active, then this is reset, and this is deasserted. The problem is because now it's synchronous, the Vivado will actually try to optimize this, because the requirement here for this net is it's activated here, and this edge is activated here, but must be at all destination at this edge. This means the total time is T, the period of the clock. To be, this means that there's a requirement for all of the signals here. It must run with, let's say, 100, 200 megahertz. Very, very strange and very, very hard requirement. So that's actually the disadvantage. If you have a big global reset, then you end up with optimization of, and these are thousands of nets. Very, very bad. Don't do this. That's a disadvantage if you do a global asynchronous reset through a reset bridge. Okay. So what could be the alternative is something like this. You just do a so-called clock gating. You have the reset. Okay. You just activate the reset, and that's a reset generator is doing this. Whenever you activate the reset generator just use above the switch off the clock. Okay, this means this, because you switch off the clock, there is no clock signal here. Now, the reset have enough time actually to propagate, because there's no clock, there's no timing variation if there's no clock. And when you deactivate the reset later, okay, then the reset will be deactivated, but the clock is still disabled. Once after a while, then the reset generator will again enable the clock, and then the reset signal is stable. It's called the clock gating. This is actually described here. So this is one of the application, clock gating during reset removal. Very, very nice structure here. And this is actually just give you some information about RAMs. I'm running a little bit out of time, so I have actually prepared actually some two examples, but I will do the example in the next second part. Actually in 2 weeks I run the second part of this, and then I will actually present the example, because sorry, I'm running a little bit out of time, but at least I give you here the information about the block RAM. So we do have some block RAMs and some FIFOs in our design. This means these can be used in order to store data, one as a RAM approach and one as a FIFO approach. Okay, so for example, what you can do for the RAM, even if you do the RAM has to is actually standard is a dual port. This means port A, port B. Okay, we can change the ratio size to width. We have two different clocks, so we're through dual ports, so two different clocks, and so this means you do have a very, very multiple configuration for such RAMs. Okay, we can also integrate, combine several such block RAMs to build more complex RAMs. We can use the integrated error correction, detection, and correction circuit. This might be for some safety critical application, might be of interest. We can also have byte write enables. This means if the block, let's say, block size is 16-bit, but I want like to actually write all the 16-bit, and you can actually generate byte write enables, so you can write 8 bits instead of 16 bits. So, and once a block RAM can be used in two different let's say applications. Could be used as two independent single port 18-qubit block RAMs, or can be used as one 18-qubit block RAM and one FIFO. Okay, so between two smaller block RAMs or one small block RAMs and one FIFO. That could be done. This means what you can do, you can configure this block to be one single port, one in and one out. Simple dual port is port A input, port B output, or dual port RAM. It is input and output, and input and output. Okay, and these are the different. You can split it to smaller units, or you have the big stuff. So, and actually, again, I prepared some examples how to access this type of RAMs, but I will present this the next time. And the FIFOs is actually, well, it's just a different storage. So now we just write in data here with a clock A, right clock, and read the data here with the read clock. This is not shown, but it could be the same clock, or could be different clocks. In this case, this picture is for the same clock. Usually, we have two different clocks, one right, one read clock. Okay, so very nice. You can also combine the FIFOs in depths and in widths, and this means completely different operations here. Okay, and that's actually the internal operation. So we write the data and we read the data, and you see usually we do have two different clocks. So it's a very, very nice communication between two independent clock domains. That's actually the FIFO. The concept of the FIFO you would need. So sorry, I was a little bit out of time here, so sorry for this. But just if you need more information, just do a copy or just scan this code. Then you will actually have a more additional information. I hope you liked my first webinar again. So thank you very much for your attention. I hope you enjoyed the webinar, and I see you next time for the next event. And goodbye.